In this video, we're going to look at power series. So first off, what is a power series? A power series is an infinite sum of non-negative integer powers of x. It's a power series because I have integer powers, and I can write that as p of x equals a naught plus a1x plus a2x squared plus a3x cubed, and it keeps on going forever and ever. So I can get the general term is a n x to the n, or I can write it a little bit more simply. It's p of x is equal to the sum as n goes from 0 to infinity of a sub n x to the n, recalling that x to the 0 is 1. Now, we're going to see a couple examples of power series that have a little trick using long division, and then we'll use some of this idea more to deal with Maclaurin and Taylor series. So first, we'll use long division to find the power series for f of x. And usually, when I did long division, I would do 3 divided by x plus 1 in standard form, and notice that I can't have a whole power of x go into 3. I'd have to sort of have a x to the negative first going on here to make that work, and so this would usually be my remainder. But if I do this, instead of considering this as x plus 1, as x plus 1, I just use the 1 plus x, I can do some useful math. So I say, how many times does 1 go into 3? Well, 1 goes into 3 3 times. I multiply this by that expression, get 3 plus 3x. I subtract, the 3's cancel, and I get a negative 3x. And I can actually continue. 1 goes into negative 3x, negative 3x times. And I multiply this by that expression, and I get negative 3x minus 3x squared. And when I subtract this, the negative 3x's cancel, and I get a positive 3x squared. And so 1 goes into 3x squared times, and you can probably see the pattern. I'll do it one more time. Multiply through 3x squared plus 3x cubed, subtract, cancel, bring down the negative 3x cubed, and we can see, okay, the next term is going to be plus 3x to the fourth, minus 3x to the fifth. But the question is, how do I represent this pattern in a general sense? And here's the idea. So see that every term has a coefficient whose magnitude is 3. So I'll have a 3. It alternates, so I'm going to have a negative 1 to the n power, and I need to be careful that I get it to start off correctly, so I might need to change it to an n plus 1 depending on whether I want this to be negative or this to be negative. But we'll check that before we move on. And I start with x to the 0, x to the 1, x to the 2, x to the 3, x to the n. And just checking to see if this actually is the case. So p of x equals the sum. This is positive and has x to the 0 power, so I will start n equal to 0. This just makes sure I get the correct starting term going off to infinity, and 3. And I can have negative 1 to the n x to the n, or since they're both to the n power, I can actually write that as negative x to the n power. And this does generate that power series. Now, the obvious question is, why? Why would I do anything like this? So why would I take this function, which seems relatively simple, and turn it into this infinite series. And the simple answer, my personal thought is, for a simple rational function like this, I probably wouldn't do this. However, this process, getting to an infinite series, can be exceptionally useful when I get to transcendental functions, sine, logarithm, e to the x, these various things. So this is the power series. Let me go to a new slide and look at what happens for the convergence of this, and then I'll show you graphically what's going on and how it actually fits all together. So we see that my power series, so p of x, is equal to the sum, as n goes from 0 to infinity, of 3 times negative x to the n. And if I want to see where this converges, the interval and then the radius of convergence, I can do the limit as n approaches infinity of the n plus first term, so 3 times negative x to the n plus 1, divided by the nth term, 3 times negative x to the n. I see that the 3's cancel, and there's one additional negative x in the numerator. So that limit is equal to negative x. This will definitely converge between negative 1 and 1. When I divide through the entire thing by negative 1, these switch signs, and the inequalities switch because I'm dividing by a negative number. And I would rewrite this as negative 1 is less than x is less than 1. From this, I know that the radius of convergence is equal to 1. I still need to check to see if I have any equal to part here. So when x is negative 1, this is just going to be 3 times 1 to the n, which is going to be 3 plus 3 plus 3 plus 3, diverges. When x is positive 1, this will be 3 times negative 1 to the n, which would be 3 minus 3 plus 3 minus 3, still diverges, so this is the interval of convergence, and that was the radius of convergence. And now the promised what's happening here. So let's flip over to this. So this green curve is 3 over 1 plus x. And this here is just the first term from our power series. This is just 3. Now, as I increase k, I'm going to add on more terms. So this originally was just p of x equals 3. If I add on another term and get 3 minus 3x, I get this. And as I add another term, 3 minus 3x plus 3x squared, I get this. And what you can notice is I'm switching from odd to even functions over and over again. So third power, fourth power. But the curve, the gray curve, which is a polynomial estimating the power series, is getting closer and closer to the green function. As I add more and more terms, you can see that over here especially, it's behaving better and better. But only up to a point. So I can keep on adding more and more and more terms, but notice, it's never getting better outside of negative 1 and 1. And that's because it only converges between negative 1 and 1. So over here, it's never approaching this area over here. It's actually getting worse to this area out here. But as I do this in the interval negative 1 to 1, in the interval of convergence, the series converges to the function. And actually, the infinite series would equal the function. So that's what's going on here. That's how this stuff all plays a role. So if I have on 50 terms, you can see how close it is. All right, let me reset this for our next problem. All right, so that's what went on in the first problem. Now let's look at another example, see how the same stuff happens. So in this, use long division to find the power series for this. So I will divide, change back to purple, so I have a 1 minus 2x squared, and I have a 5x inside. So different, but not hard. 1 goes into 5x, 5x times. And I multiply through, and I get 5x minus 10x cubed. Subtract, 5x's cancel, I get a positive 10x cubed. 1 goes into 10x cubed times. Looks a little bit weirder. Multiply, I get 10x cubed minus 20x to the 5th, and subtract, these cancel. Negative, negative gives me a positive 20x to the 5th. So I get a plus 20x to the 5th. You may see the pattern. Let me show just one more step down here so we can really see what's going on. So 1 goes into 20x to the 5th, 20x to the 5th times, and I multiply through. So 1 times 20 is 20x to the 5th. 20x to the 5th times negative 2x squared is negative 40x to the 7th, and I subtract. These cancel, and I get a positive 40x to the 7th. So 1 goes into 40x to the 7th, 40x to the 7th times. And let's look and see what's happening. So 5, 10, 20, 40. They're multiplying by 2 each time. The next one's going to be 80. X to the 1st, x to the 3rd, x to the 5th, x to the 7th. These are the odd powers. So in here, the general term, if I want to get an odd power of x, I'll do x to the 2n would give me even powers, plus 1 give me odd powers. When n is 1, this is 3. When n is 0, this is 1. Okay. I start off with a 2, and then I multiply by 2 repeatedly. So I start with a 5 and multiply by 2 repeatedly. Multiplying by 2 repeatedly is 2 to the n. When I multiply 2 by 2 by 2 by 2 by 2, I get powers of 2. But I start off with 5. So I'm going to do 5 times this. So the power series of x will equal the sum as n goes from 0 to infinity of 5 times 2, I don't need the parentheses there, times 2 to the n times x to the 2n plus 1. Okay, and I can check, so if I put in 0, 2 to the 0 is 1, 2 times 0 is 0, plus 1 is 1, so I should get 5x, and I do. When I put in 1, 2 to the 1st is 2, times 5 is 10, and 2 times 1 is 2, plus 1 is 3, so I get 10x cubed. Now, let me consider the interval of convergence for this, which is going to be a little bit weirder. So I have p of x equals the sum as n goes from 0 to infinity of 5 times 2 to the n times x to the 2n plus 1. And I'll do the limit test. So limit as n approaches infinity of the n plus first term, so 5 times 2 to the n plus 1 times x to the 2 n plus 1 plus 1 all over 5 times 2 to the n times x to the 2n plus 1. Now I can see straight away the 5's cancel, and I have 1 extra 2 in the numerator. So I have this limit as n approaches infinity of, I have 1, 2 in the numerator, nothing left over here, and let me distribute this through, so I get x to the 2n plus 2 plus 1 is going to be plus 3 over x to the 2n plus 1, which leaves me with 2x squared. Because I have 2 extra x's. I have 2n plus 3, 2n plus 1. When I'm dividing powers, I subtract their exponents. And I can put this between negative 1 and 1. And in here, so I'll divide by 2 and get negative 1/2 is less than x squared is less than 1/2. And here's what happens. It's a little bit weird when we see it at first. I need to get rid of the squared, so I'm going to try to take the square root, but this form right here, of course, is complex. If I'm only dealing with the real calculus, I don't have any negative squares, but whenever I get rid of a squared, I have the plus or minus, so I really do get to the negative square root of 1/2 is less than x is less than the positive square root of 1/2. They actually both come from this bound. We don't get anything to this side. It's actually going to be bounded by 0. And let's see graphically what's going on. So, this is the interval of convergence. The radius of convergence will be the square root of 1/2, which you could, of course, write as 1 over root 2, or if you rationalize the denominator, root 2 over 2. They're all the same. Most math teachers like this. The AP test has eased up and is probably fine with this. They might not like root 1/2. All right, graphically. So get rid of these functions. Here is 5x over 1 minus 2x. And here is, if we have 1 term, 2 terms, 3 terms, 4 terms, and it gets better and better and better. And 1 divided by root 2, or root 2 over 2, is somewhere about, 0.7. So you can see from x equals negative 0.7, approximately, to x equals positive 0.7, the function behaves very nicely. This red is getting really close to this orange, but as I go out beyond that, it's never approaching these. All right. I hope this was helpful. Feel free to comment below if you have any questions.